is something along the effect of stags, hawks, and doves, social evolutionary theory, and individual variation. So folks have been interested in social evolutionary theory for a long time, and one of the crucial aspects, though, we're starting to really get into to think about is how does variation in social evolution work? And this kind of comes from folks being interested as well in how variation in personality and variation in other kinds of behaviors evolve. But one thing that we can really do when we start to think about how that natural selection creates variation in behavior, when we think about social evolution, is we can look at the tools that we've used before to study social evolution, such as game theory. So so folks are probably familiar with things like the prisoner's dilemma, which is kind of a classic game in game theory. And if you set up sort of a prisoner's dilemma, you often have a case where you have sort of a benefit for cooperating, you have some kind of unconditional cost for cooperating, and then you have as well, and so the contrast of those two things, the benefit and the cost, means that individuals will tend to be selected, if there's sort of no other effects in play, tend to be selected to not cooperate. So what you can do is you can sort of look at that kind of more general scenario where you have a payoff matrix, the benefits of cooperating if you're two cooperators, the cost of cooperating, and then it's not paid by a cooperator. And you can allow those payoff values in the matrix to change. And so when you allow those those values to change, you essentially get three other kinds of games. You get a game called a stag hunt game, which is where individuals who can be sort of either selected on their initial conditions to either cooperate, both of them, or not cooperate. It's often called a coordination game. Or you can get a hawk-dove game. And a hawk-dove game is sort of one of those classic games from that early Maynard Smith paper. In that case, you get an intermediate value. You get cases where individuals either sort of cooperate, some of them, and others don't cooperate in the same population. So this kind of sets up a scenario for a kind of polymorphism in social behavior within the population. So that's sort of in contrast to what you get for the stag hunt game, where you have some populations maybe where all individuals are cooperating, and other populations where all individuals are not cooperating. So that's kind of a coarse scale between population level variation and cooperation, whereas this hawk-dove game sets up more within population level of variation and cooperation. So by simply sort of changing the values of the payoffs in the payoff matrix, you can sort of shift between kind of a prisoner's dilemma, there's no variation in cooperation, you just have all individuals defecting, to if you allow for cooperation to actually be individually beneficial, you can have a mutualism game, there's still no variation, but individuals are all cooperating in the population, to these two other kinds of games, the hawk-dove, where there's within population variation, and the stag hunt, where there's sort of some populations cooperating, others not. And so this is sort of, while this has kind of been done before, one sort of thing to add in is allow for the fact that you can change those payoffs really are actually not sort of just ecological payoffs or measures of increase of sort of food or help from a partner, but they're really fitness quantities. So we can change fitness quantities in all kinds of ways. And one of the important ways we can change fitness quantities is by altering, for example, the demography of the population. And those demographic consequences will sort of change how fitness feeds back to individuals. And the big way to change that is to change population structure. And we do that by changing dispersal rates, or something that affects genetic relatedness. So in that case, that recalls the idea of Hamilton's rule. So if we sort of go back to that classic work that suggests that if you have individuals sort of in a patch and they're highly enough related to one another and they're not competing too much for resources locally in that patch, then as long as that relatedness value is strong enough and the benefits of cooperation are strong enough, those can outweigh the costs, and you'll get the evolution of costly helping. So by sort of tweaking that relatedness coefficient, making it higher, you can get for cooperation, making it lower, you won't get any cooperation. But as well, that can actually then shift, so that's shifting just between actually those values of those payoffs essentially, and shifting between, for example, a mutualism game where you have all cooperation, and then a prisoner's dilemma where you have no cooperation. So it turns out that what you can combine that with another effect. So the sort of one effect that we haven't talked about so far is the effect of payoff synergies. So often when you think about individuals cooperating, and that's sort of that very simple matrix where you've got benefits and costs, is that not only can you have an additive benefit of just what I get or what my partner gets when I invest, but when we invest together, there might be some kind of nonlinear effect of that combination of our two investments. So this is often we call synergy. If it's positive, then it's sort of saying that the sum of our our investments are greater than the sum of our two individual investments. And if it's negative, there's actually some kind of destructive interference when we both sort of invest in that cooperative activity. So when there's actually positive synergy, it turns out you get sort of a regime where you can get this stack hunt game where you end up having individuals sort of all in the right situations or the right initial conditions, all being selected to all help. And in other cases, they're being selected to all not help, so you get this between population level variation and cooperation. And when there's negative synergy, then that's sort of that case where there's this destructive interference between the investment activities of the two individuals who might be helping. And you get this kind of hawk-dove interaction. You get fine scale variation, so some kind of polymorphism within the population. And these things are both possible when you sort of tune relatedness. When relatedness is really high, there's sort of an underlying incentive, an evolutionary incentive to invest in cooperation. And with some negative synergy, you can get this fine scale variation. You get a hawk-dove game evolving. But when there's low relatedness and you have enough positive synergy, then what you end up getting is there's not really much incentive initially to cooperate, but if the initial conditions are right, all individuals in the population will cooperate, and if their initial conditions are not right, no individuals in the population will cooperate. So you get that kind of coarse scale variation. So the sort of general pattern is low relatedness and high synergy. You get sort of between population variation and cooperation. High relatedness and low synergy, negative synergy, you get within population levels of variation. So one other thing that you can add that's sort of one of the sort of other really classic mechanisms to allow for cooperation in general, other than sort of just population structure and relatedness, is the ability of individuals to respond to one another in real time, to have some kind of reciprocal interactions, like reciprocal altruism. So in those cases, then, you can sort of you have the same kind of intuitive understanding, which is that if you have enough of this responsiveness, then you'll go from a situation where you have a prisoner's dilemma and no cooperation to having a mutualism game and full cooperation in the population. So you can play essentially the same game and see how you can intersect the ability of the fact that reciprocity can generate cooperation with the fact that there might be non-additive or these synergistic payoffs. And you get essentially the same kind of picture. When there's very little reciprocity allowed or very little sort of this behavioral plasticity in the population, then if you have high synergy values, you sort of have positive constructive interference in the investment of two individuals, then you end up getting this stagnant game, and you get this core scale variation in cooperation. Some pops cooperating, other populations not. And then again, the same thing, if you just sort of increase the level of responsiveness to make it high, then the sort of underlying incentive, the fitness incentive, is to cooperate. So to get variation, you have to have sort of this negative synergy, which if that's high enough, then you get that same sort of scenario where you have now fine scale variation, you have potential stable polymorphism in the population. And then finally, you can sort of combine the two of those effects. So you can allow for the fact there might be some population structure, there might be some behavior that creates relatedness, there might be some behavioral plasticity that creates reciprocity or responsiveness. And in those two cases, then sort of any amount of those two factors alone will sort of create a really wide range of parameters where cooperation is stable. And there's no variation in cooperation in the population. But the one case where you can get it is if you now, because there's that underlying incentive to cooperate, if you just decrease the synergy, you make this sort of destructive interference between the investments of the two cooperating individuals, then there's actually some range of parameter space where you can have this hawk-dove game, where you can have this fine scale variation in cooperation. So the sort of upshot is that you can sort of switch between these four different kinds of games, and you can sort of see what are the selective conditions where you can get cooperation, variation of cooperation or not, as a function of not just the payoffs, but as a function of other sort of demographic parameters that change relatedness, and as a function of how sort of behaviorally plastic individuals are. So this sort of sets up a situation where you can have make some kind of comparative predictions about where you might expect variation in social behavior, variation in levels of cooperation, either sort of within populations, or maybe where you expect variation in cooperation to exist between populations, or between even maybe sort of closely related species. So the case where you might expect variation to exist between populations, you think is going to be more likely based on these results in cases where there's sort of relatively little population structure and relatively low levels of behavioral plasticity or reciprocity. But you're going to have some kind of high level of synergy. So you might think of, for example, one example of this is something like like cooperative hunting. So where sort of additional investments of effort by individuals in the group may yield sort of an even larger increase in the ability of the group to take down prey. In that case, you might be able to see that in some cases, some groups, just because of the sort of initial condition of the individual's behavior in the group, they're able to all sort of reach this all coordinated, all cooperate equilibrium, and they're all able to go on a cooperative hunt, and other groups just aren't able to get off the ground and get going. So you'll see that sort of between group or between population variation and cooperation. So then the other case where you get the fine scale level is where you have, again, sort of relatively some combination of at least enough relatedness or enough responsiveness, and then you have these negative synergistic effects. So one example of a negative synergistic effect might be some kind of alarm call behavior in, say, a nest of voles, or some other sort of cooperatively breeding, or not so cooperatively, but some other kind of population. So the issue in there might be is that emitting an alarm call for a predator, it sends out information to your other nestmates that there's a predator nearby, and so you sort of incur some kind of cost on yourself from the potential alerting the predator to your presence, and you have some benefit to your nestmates. But in a nestmate eliciting an additional or emitting an additional predator call might not tell many more individuals in the nest that there's a predator around, and may just simply sort of increasingly draw the predator towards themselves. So that would be sort of a case of negative synergy. You might expect to find in those cases then, no matter sort of the initial conditions or sort of fine scale variation of the population, you might expect that all of those kinds of scenarios, you find some within population variation where some individuals are emitting the alarm call and other individuals aren't. So I think I'll close it there, since
Excellent job without slides. Admirable. So if I got it, you would tune things like the migration rate and the dispersal rate, but I was wondering if you looked at how it would evolve within a system like this. Because it might be cool to see, does it go
not sort of, in this problem that requires a lot more work to sort of look at the evolution of dispersal rates.
Yeah.
If they change the sort of the relatedness, so it's the sort of second order effects of these kinds of to actually look at like the ESS value of it, yeah, you have to look at second order terms. But so yeah, the first step was just sort of to create kind of a phase space of that, to
That's
sort of
right.
see how it changes. But yeah, that's the next step to look at.
That'd be cool.
Yeah.
So you gave an example of negative synergy. What's a good natural example of positive synergy?
Oh, so the positive one might be like cooperative hunting or something where with sort of an additional, so cooperative hunting, you might imagine that like 3 or 4 individuals might have an ability to take down, they can take down instead of 4 times the number, or per unit, 4 times the amount of prey, they can take down 5 or 6 times the amount of prey than just one individual by itself. So as you sort of increase that investment, or increase the number of individuals, if the payoff increases faster than linear, faster than just a straight line, then that's an example of positive synergy. And so they may not; there may be fewer cases of that. I don't know. Than just sort of that's kind of an open question. Like, what are the different kind of economies of generating benefits in cooperative behaviors? But it becomes super crucial when thinking about whether there's going to be variation or not, and what kind of game you're talking about. So, because almost certainly most of those situations are not going to be additive. There's going to be some kind of interaction effect between individuals. Cool. Thanks.